So welcome everyone. I'm very pleased to introduce our speakers today, so Nicolas Chopin and Hai-Dang Dau. So Nicolas did his PhD in France and has been a lecturer in Bristol a few years back, but has been since 2006, right, Nicolas? A full professor of statistics at ENSAE. So ENSAE is what we call a grande école in France, in Paris, or in Paris suburbs now. And so it will be presenting a joint work with Deng, who's doing his PhD with Nicolas at ENSAE on the surprisingly overlooked efficiency of Sequential Monte Carlo. So very teasing title. Nicolas, the floor is yours. Thank you so much for being here.
So thanks for inviting me. It's always nice to present this kind of work, but please don't hesitate to interrupt me at any time and to ask questions or to make comments, etc. The more interactive, the better. I have the impression that, first of all, I'm a bit tired, to be honest. I'm suffering from insomnia at the moment, so I don't want to drone on and on. So it might be better. I might be not so clear, so it's okay if you interrupt me, if you ask me any clarification. And second of all, I have the impression that it's best for everyone if we make this online seminars a bit more interactive. So anyway, as
I much agree.
As Benjamin mentioned, this is joint work with Deng with us, and Deng will give a second part of his talk. And what I want to do today is to give you a general overview of what I call SMC samplers. I'm not the only one to call that SMC samplers. And I think they are a bit overlooked in the literature. I mean, people still rely a bit too much on MCMC or other methods. And SMC works great for a variety of problems. And second part, we will present with Deng some improvement we design to make SMC work better, or more precisely to obtain optimal performance with less work from the user. Right? You know, in science, laziness is a good thing. You should always have more automatic algorithm, etc. That's about it, to make SMC samplers a bit more automatic. Right. Before that, just in case you'd like to do a postdoc related to SMC samplers and or time series analysis for finance econometrics, we are advertising Andras, Jeremy, and me a postdoc position to work on a project we have together. So if you're interested, let me know, and I will give you more detail. But Andras is at ESSEC and Jeremy is at ESSEC Singapore. Right, and as I said, this is joint work we've done, but Deng will give a second part of this talk. And this is the two parts of the talks I've just described. First, overview SMC samplers, because in my experience, not so many people are aware exactly what are SMC samplers. And second part, the improvement, which we called Ways 3 SMC. It's a paper on archive, and it is a major revision at RGRSSB. Right. Okay, so my friend and co-author Miros Papaspiliopoulos gave a talk recently, and he started talking about tales from the crypt. So I really loved the expression. And by tale from the crypt, he meant statements in the literature which are so vague or so broad that they are not even right or wrong. They're just, they might be right in certain settings and not in other settings, right? So one of these tales from the tip you heard often is that variational base is always faster than MCMC. And Miros in his talk gave a situation where he managed with colleagues to design MCMC samplers that actually are faster than variational base and yet more accurate, right? So that's the tale from the crypt. That's not the one I'm going to discuss today. Another one is about the better mixing of HMC relative to random walk Metropolis. I will not talk about that. I could tell a funny story about someone getting very angry about the statement that this is a tale from the crypt, but this is not the topic for today. This is more relevant for today. There are many people when they hear SMC, they think we're talking about hidden Markov models. And that's fair in a sense because SMC and particle filters are closely related. Sometimes you use one to mention the other. But I'm going to discuss today sequential algorithms you use for problems that are maybe sequential, maybe not necessarily related to either Markov models. Okay. And the fourth tale from the crypt, which again is relevant to us today. There are
I think someone has the mic open. Could you please mute yourselves? Oh, Anna,
okay.
could you maybe mute them, because I can't do it.
Sorry.
I thought it was a question, so I was a bit worried because I could not understand it. Anyway, fourth and last tale from the crypt, you will see SMCs based on import sampling, and there's maybe this perception from some people that because of that SMC suffers from the curse of dimensionality. It really depends which kind of problem you look at and which type of sequence of distribution you look at. Yes.
I think it's Eugene Sun needs to mute.
Yes. Anna, could you please?
I'm trying, but I can't see the thing for muting. I'm very sorry. Hold on. Can everybody please mute themselves unless you are a student?
I'll put music instead. That would be nice. I won't dance, I promise. Anyway, so in case you're not so familiar with what is SMC, or an SMC sampler, should I say, it's an algorithm that mixes important sampling and MCMC techniques to approximate a sequence of distribution, right? So in some problems, you do want to approximate several distributions sequentially, all right? That's the perfect tool for the job. But we also discussed some other situation where you have a single distribution of interest, and you may still want to use SMC. The trick being that you're going to design a sequence of distribution that starts from some simple distribution and that ends at your distribution of interest, okay? And that's an interesting approach, I think, okay? So as I mentioned before, SMC samplers are maybe for both sequential problems and non-sequential problems. Before I describe it, some nice properties of this algorithm. I hope you see my pointer when I move it, when I show some part of the slide. Yes?
We do, yeah.
Yeah. Okay, so you will see that essentially you just need to be able to compute the density of the target densities pointwise up to a constant. So that's a small requirement. This kind of algorithm is easy to parallelize. And actually, I do it personally, and Don can tell you he does it as well. It's really easy to parallelize this kind of algorithm. You get estimate of the normalizing constant, which are very useful in many settings, like in model choice, for instance. You will see that these algorithms are quite automatic, adaptive. They have tuning parameters that you can set automatically. Okay, that's related to the second part of the talk. And more importantly, they are competitive to other methods. So I have this paper with James Ridgway where he compared many different approaches to do Bayesian logistic and probit regression. It's partly a review paper, partly a discussion paper about what it means to use logistic regression as a benchmark for Bayesian computation. I hope this paper is a nice introduction to Bayesian computation as well. But you can see in this paper that SMC samplers are quite competitive to other approaches. And also there's this paper where we managed to push SMC samplers to dimension 4,000 or something. Okay. Anyway, to make the discussion a bit more concrete, here's a kind of Benjamin, this is for you. Huh? You noticed I prepared this slide for you.
I'm very, very flattered.
Okay. So you guys with Benjamin, you work on packed Bayesian learning. So I'm not going to learn anything from this slide. But when you do packed Bayesian learning, you have this kind of pseudo posterior where Rn theta is empirical risk. And one of the problem, I think you will agree, is how to choose this lambda here. Okay. And you could use SMC, where you will consider a sequence of lambda values starting at 0. So at 0, you just have a prior, and then you increase lambda, and then you manage to approximate all these different pseudo-posteriors, and in the end, maybe you can choose lambda based on some criterion like a cross-validation, right? So what SMC gives you in this context, especially compared to MCMC, is that you manage to have an approximation of many different pseudo-posteriors for different values of lambda, okay? So which I think is very nice, okay?
So Nicolas, sorry, I have two quick questions on the slide. So you don't renormalize by n your empirical risk, so you integrate in the lambda the effect of the sample size. Is that right?
Yeah. Yes, maybe. No, you could divide Rn by n, and then it will change the values of lambda you will consider. Yeah.
I'm asking because in SMC settings, typically you would assume that the sample size is fixed, right? So we not try to be kind of adaptive with respect to n changing very much.
No. Right? And in this, what I have in mind here is that your data set is fixed,
right? And
you have the only thing is going to change is lambda. You just want to approximate your pseudo posterior for different values of lambda.
Right. Okay.
So you have maybe a maximum value you want to consider, and maybe you're right. You should divide this by n. Sorry, and but then the discussion will be the same, right? Okay.
Right. I think I'll save this one question for later because probably this is going to kick in. Anyways.
Okay.
May I quickly ask? Are we meant to know what sequential Monte Carlo is already, or?
Just bear with me.
Okay, all right. Sorry.
For what I'm describing what for, but I will describe it in a moment. Thank you for your enthusiasm. Anyway, there are people actually in econometrics who do also this kind of thing. I don't know if you're aware of this, but like Shanozukov and Hong. But anyway, that's less relevant to you guys, so I mentioned this quickly. Sequential learning is another kind of problem when you might want to use SMC. Imagine you have some parametric model and your data arrives sequentially, okay? And then if you're a Bayesian, you might want to consider this sequence of this sequence of actually G9 in a posterior distribution. So again, this will be your prior. That will be your likelihood given your parametric model with this data. And you would like to approximate the prior, the posterior given the first point, the 2 first point, the 3 first point. So if you want to do sequential learning, then SMC is the right tool for the job. Alternatively, perhaps you're not interested in sequential learning. You just want to estimate the parameters from a complete data set, and you can still use this approach, but you just use the result from the last step. Okay. And I don't know if anyone works on ABC in this group. But yeah,
I think a few people are close to ABC. I'm not exactly sure working directly on ABC, but
okay. So ABC is this kind of method where you describe the model only through a simulator, right? You have this whole piece of Fortran code that simulates this very big complex system that your colleagues in physics gave you, and this piece of code takes as an input some theta. And the only thing you can do is to generate data points given theta. And then you have all this class of algorithms called ABC, where basically what you do is that you try to change theta, and for each theta you try to simulate y's until they are close enough to y star, which is the actual data. Okay, and that's a typo, and I suspect I have a problem with my Dropbox and I don't have the last version of the slide. Sorry for that. But anyway, in the context of SMC, maybe you can use SMC with decreasing sequence of epsilon, right? Like maybe you could take epsilon 0 to be plus infinity, and then this should be just the joint distribution of theta and y. And then you make you make the constraint stronger and stronger, and you make the region smaller and smaller. Okay. And again, maybe you don't have a sequence of distribution. You just have some target density, right? So pi of theta, some target density, which I managed to rewrite like this, right? So mu theta is some over density, like a base density, maybe a Gaussian. And this x minus v of theta is just the ratio between the two. Or v of theta is minus log the ratio, right? So it's just rewriting things, right? But at the end of the day, you just want to sample from pi or compute the normalizing constant of pi. And then you have this sequence I really like, which I recommend a bit by default, which is the tempering sequence, where basically you have a lambda here, and you'll take lambda at 0 at the beginning, and then you will increase lambda progressively until it reaches value 1. Okay, so again, you see at the beginning of the algorithm, you're going to sample from mu, and then at the end of the algorithm, you will sample from pi. Okay, and you're doing linear interpolation on the low scales, so to speak. So I apologize for the person who asked me to describe SMC. You have to wait a few more minutes. I'm still doing a quick few remarks regarding tempering, but again, bear with me. So this is just a tempering sequence. Imagine your initial distribution is this Gaussian, right? And that your pi is this mixture of two Gaussians. And then this intermediate lines here are the tempered distribution for lambda equals 0, 0.1, 0.2, etc. All right. And before I describe the algorithm, I just wanted to say the reason why this tempering sequence is particularly nice, I think, is first that we already know, but has been ideas about this has been around for quite a few years. There are ways to choose these lambdas automatically. Okay, so if you know parallel tempering, you have a similar ID. But here, what is very nice is that you will have a simple way to choose automatically the next lambdas, right? So, and this is very important for performance. If you try to choose it manually, it will be terrible. And if you do use this kind of automatic tuning, it will work really well. Right? So it is important. And second point, which is not so well known, and so I have this recent book with Omiros on SMC methods, and I wrote that in the relevant chapter, is that what is very nice about tempering is that imagine you have two Gaussian distribution in dimension D, okay? And you're trying to do tempering from Gaussian A to Gaussian B, okay? If you like to do important sampling directly from A to B, you will have a curse of dimensionality. This is well known, and basically one way to formalize this curse of dimensionality is to say that the chi-square distance between the two distributions is exponential indeed. The chi-square distance is strongly related to importance sampling because essentially it's like it's related to variance of the weights. But essentially, in more practical terms, if you try to do importance sampling from A to B, the most of the weights will be 0, and very few of them will be 1. Okay, but if you allow me to use a tempering sequence of intermediate distribution, okay, you allow me to have square root of D intermediate distribution, then I'm able to choose this intermediate distribution along this tempering scalar so that the chi-square distance between two successive distributions is 2 of 1. Okay, so in more practical terms, this means when in large dimension spaces, when you do important sampling, you suffer from a curse of dimensionality, yes. But if you allow me to do tempering, there might be a way around because I don't need so many intermediate distribution, so that doing important sampling from pi 1 to pi 2, then from pi 2 to pi 3, each time the variance of the weights is going to be small. Okay, so this is very nice.
Nicolas, I have a question related to that. So that's not accounting actually for the cost of sampling for each distribution, right? So it's in particular interesting if the cost of sampling each distribution is less than something, I gather.
Yeah.
Is that right? Okay.
For the moment, I'm just saying if you had some magic way to sample from each pi t, then going from pi t to pi t plus 1, the variance, the importance sampling will work well. Yeah, I'm just saying that. Yeah.
Thanks.
Anyway, now I describe SMC. Finally, sorry for that. Imagine you have a sequence of distribution pi of t. Okay. For the moment, It's easier.
I'm sorry, we can hear your mic, Keshav. Would you please mute yourself?
Sorry, can I just request we mute all the participants except the speaker because this has been repeated now?
Yes. Anna, I don't know if you can do this because I can't. I'm not a co-host yet. All right, seems good now. Thanks. Please go on, Nicolas.
Yes, so I was saying, imagine you have a sequence of distribution, pi of t. Naive algorithm will be, you start sampling from pi naught, theta n times. Then you do important sampling from pi naught to pi 1. This means that for each particle theta n, random variable, you compute a weight which is proportional to the ratio pi 1 over pi 0, pi naught. Okay? And then naively, you could say, oh, but not to move to pi 2, I'm just going to reweight according to pi 2 over pi 1. And of course, the problem with that is that this ratio cancel, and in the end, it will be equivalent to important sampling from pi naught to pi t. So you're not going to escape the curse of dimensionality of important sampling. Okay. So we are going to do something a bit more clever, which is we have a sequential algorithm like that. At time t-1, you obtain a weighted sample that kind of approximates pi t-1. Formally, this means that when I compute this kind of weighted average, so theta t-1 n, they are my n particles at time t-1. They have a normalized weight like this, right? You see this weights they sum to 1. And this kind of weighted average approximate the expectation of phi with respect to pi t-1 for the moment. To go to the next stage, what you do is that you're going to resample, which means drawing with replacement according to the weights. And then each particle will be moved according to an MCMC kernel that lives invariant pi t-1. So because of lack of time, I will just call on your intuition. It's quite intuitive that if this weighted sample approximates pi t-1, each operation will be such that you still approximate pi t-1, yet doing the resampling step, you're going to kill the particle with the low weights and reproduce many times those with a large weight. And then by doing this MCMC step, you're going to rejuvenate the sample. I mean, you might have some of them that got several identical children, but then through the move step, they are made different. Okay, so that's the standard SMC sampler framework, right? You do important sampling and resampling plus MCMC. But the way we do MCMC is quite novel, or it's different from what we used to, because you don't have one single long MCMC chain. You have many particles and you move them according to one or small number of steps. Okay.
So,
yes.
Yeah, sorry, Nicolas, just to clarify things. So you do have one MCMC kernel. You don't have T MCMC kernels.
No, we do have T kernels.
Okay.
At each time.
So each time T, you get a different kernel.
Yeah, you need a different kernel at each time T because you need to live invariant pi t-1.
Right.
So yes, very good point. The ingredient for SMC samplers is that you need a sequence of distribution and you need a sequence of kernels.
Right.
And to give you a practical idea of what we can do, you could do random walk Metropolis every time. But of course, in the acceptance ratio, you use the density of pi t-1. And you can calibrate the covariance matrix of the random walk according to the empirical covariance of the particles, right? Again, this is just a basic recipe which is very down to earth. But if you don't do something like this, performance is going to be terrible. If you do it, it works very, very nicely. Okay. And the thing behind this is that random walk Metropolis is not such a bad algorithm. Random walk Metropolis is bad when you don't calibrate it well. But if you have some simple way to calibrate it, then it works nicely. And in a SMC scenario, you have a cloud of particles, so it's easy to calibrate it.
Thanks.
You're welcome.
Right, is there any chance, sorry to be really annoying, is there any chance we could go through the last slide again? Because I'm a bit lost, I must admit.
Sorry for that. So
yeah, I'd find that useful as well.
So this one? Yeah, so which part did you want?
So just to go through what things are again. So the pi's are the sequence of distributions, is that right?
Yes, so we are at time, let's say you are at time t-1, and in some way you manage to obtain a weighted sample, right? So you have weights like this, and random variables, and this weighted sample approximate pi t-1. And approximation, when you do Monte Carlo, it means this. It means this kind of empirical average for any function phi is going to approximate this.
So
Okay.
is phi your kernel?
No, phi is just any function. So for instance, you could take an indicator function, like for an histogram or, yeah.
Okay, and where do these weights come from?
So that's the thing, I'm describing the algorithm in a sequential way. So imagine at the very beginning, you sample from pi 0, and your first weights, small w, will just be pi 1 over pi 0. Okay? But then I'm just saying, imagine at time t-1, you obtain the weight in a certain way. Or do you go to same t, you do all the separation, and then you reweight according to pi t over pi t-1.
Okay.
So every time you're going to discard the weight because you're a sample, and then you're going to reweight the particles according to this, you know. So it's like this. You remember at time 0, you sample from pi 0. Then at time 1, you reweight according to pi 1 over pi 0. And at time t, you're going to reweight according to pi t over pi t minus 1.
Okay, so on the next slide, this approximate equality you've got, that's by definition, that's not a theorem or anything.
There are theorems that say something like that. But
okay.
Essentially, when n goes to infinity, this is going to converge to this almost surely. Or square root of n times the difference is going to follow a normal distribution.
And one last question, is phi is a given function, right? You're not choosing this.
Well, one way to interpret any kind of Monte Carlo algorithm is to say that you have this asymptotically for a big class of function. It's a bit formal way of describing Monte Carlo. Because when you discuss Monte Carlo, usually people think in terms of, I want to approximate an expectation and I compute some empirical average, right? But then if this is true for a large class of function, typically any function such that the variance of phi exists with respect to pi t-1 plus of the condition.
Okay.
Yeah.
Thank you.
Is there any other question?
Hi. Yeah. Could you explain again what pi of phi is on the right-hand side?
Pi of?
Yeah, this pi t-1 of phi. So
It's
phi is a function, and
so it's your problem. You wanted to approximate some sequence of distribution, pi 0, pi 1, pi 2, pi t, etc. That's what you want to do. But that's user chosen if you want.
I think the confusion might be that the notation is slightly different often in machine learning to in statistics. So I think here the right side is the integral of the function phi with respect to pi.
Yeah, that's exactly. That's the expectation of phi of x when x follow distribution pi t-1. Yeah, it's a.
Okay, that makes sense.
Sorry for that. Okay. In probability, they use it all the time. In stats, is quite common. And I did this talk in front of econometrician, and it was okay with them. So sorry, I should. Sorry for that. Sorry, I didn't realize it would be. Right, sorry. Any other question, maybe? Feel free to ask again. I mean, I'm happy to answer any question you have. Should I go on then? Or, yeah?
Oh, good, it seems. Yeah.
Okay, anyway. So I'm just checking time. So one So here I'm just describing one kind of MCMC scheme you could use. You could do Mala, HMC, Gibbs, etc. But one thing which was not so clear, I think, in the literature, including in some of my papers, is that how many steps you do. Right? You could do one step, you can do 2 steps. If you do 2 steps, that's a bit equivalent like applying one kernel, which is a composition of some simple kernel twice. Okay, so any value of k will be valid. And the performance seems to depend on k in a non-trivial way. I will show you. Right, so this is taken from my book with Omiros, and I'm not going to discuss the actual setting, but we have 2 kinds of SMC algorithm here, and here this is the number of MCMC steps, and this is the box plots of some estimate we compute from the algorithms when we execute the algorithm many times. Okay, when you do a Monte Carlo algorithm, each time you get a different answer because it's a random answer, and the bigger the variance of your error, the less interesting is the algorithm. So you can see here that if I take k to be 10, it's still too small. I still have a huge variability, and it seems that, especially for the white boxes, I need to take k quite large to get a decent performance. All right, so I'm a bit running out of time, so I'm skipping this and this, but I will go back to this if you have questions related to this. So the big question, I think, what was remaining was how do we choose k? Should we have k fixed along the across time? And if it seems that if there are problems when you need to take k to be quite large, is it not a bit wasteful to keep only the last particles? So that's where I start the second part of my talk, and I will let Dang speak in a few minutes. Let's assume that capital N is still the sample size, the number of particles, but I'm going to assume that N equals MP, where MP are two integers that divide N. What I'm going to do is to resample only a small number of particles, maybe 100. For each particle, I'm going to run my MCMC chain for p-1 iteration. And then I will keep all these intermediate steps. So here I have, in essentially, m chains of size p, because at the beginning I already had m states, so m plus m plus m. And I go back, I return, I obtain n particles. But there is no waste because I keep all these intermediate values. Okay, so essentially that was the main idea at the beginning. All right. So at the moment it might look a bit like a trick, and we have some theoretical results saying that it's actually a good idea to do that. So again, due to lack of time, I think Dang will with me. We can skip that. That's not very important thing.
Nicolas.
Yes.
Could I ask a question about something you said before? So you asked about this question about K and how large you should take K.
Yeah.
Would that not depend also on your sequence of distribution?
Yeah, of course, yeah.
Oh, okay. So you're going to tell us how to do it.
Yeah.
Okay.
Basically, essentially, it depends indirectly on pi of t. It depends essentially on the mixing of your kernels. Every time t, you have a different kernel.
Okay.
And if it mixes very fast, maybe you could take k to be small.
Mm-hmm.
But if it's very slow, then you should take k to be large.
Okay.
But the second part of the talk now is about this waste-less variant, where key disappears. You don't need to specify key anymore. Instead, what you're going to do, you'll have these two M and P, and I'm going to explain. I was about to explain that the choice of M and P are less important. So let me explain that.
Okay, thank you.
Thank you. You're welcome. So we have this kind of asymptotic result in the paper where we say that if you keep M, the number of resample particles fixed, or if you make it grow slowly, more slowly than N, and even if P goes to infinity, right? So That means the total number of particles go to infinity, but maybe the number of first sample particles you keep is fixed. Then you have this kind of central limit theorem, which is typical in SMC with this asymptotic variance that depend on time. Okay, but to make it simple, let me say this way: this asymptotic variance you get here at time t. If you look at this, if you're a little bit familiar with MCMC, you might recognize the asymptotic variance you get in MCMC. So what this asymptotic result is saying is two things. You can see that the asymptotic variance does not depend on M. So that means I think the properties of your algorithm are going to be robust with respect to M. You can take it small, a bit smaller, a bit larger. You'll get the same performance. It doesn't depend on previous iteration, which is very nice because maybe you had some internet distribution thing worked not so well. And it suggests the following interpretation. Basically, your n particles now can be seen as m independent chains of length p, which are in the stationary regime actually, right? So that's one way to interpret our approach, which I think is nice. You know that in MCMC, it's not so obvious how to start your chain, where to start your chain, sorry. It would be perfect if you could do parallel chain, but each time you start a chain, you will start from the true distribution. Well, here in this asymptotic regime, we have something like that. Why I'm saying that? Because again, we have this asymptotic variance here, which says that if you don't reweight, so this kind of weighted average of particles. Oh my God, I changed the notation. I'm so sorry. So xtn is theta tn. I'm so sorry. I fixed that, and then there was some problem with. I'm not using Dropbox. I'm using something that replaced Dropbox, but it doesn't work as well. And I think it didn't get updated. So sorry for that. Anyway, that's your. It's your empirical average of your particles. And compared to the expectation you want to approximate, essentially here it behaves like, I mean, since this is the asymptotic versions of MCMC chain, you will get the same asymptotic variance. You had M chains independent with the same kernel with this asymptotic variance. Okay, I'm not sure it's clear, but let me know if otherwise. Yeah. And one nice extra we get from this is that there are known methods to estimate the variance of an output of MCMC chain, and we can adapt those to obtain variance estimate from a single run. So you run your algorithm once, and you get some estimate of the variance of any Monte Carlo estimate you compute from your algorithm. So in more practical terms, that means that whenever I compute a Monte Carlo approximation from my algorithm, I can also compute a confidence interval, okay? Which is not the case usually with SMC. Right. So anyway, from a practical point of view, our recommendation based on this asymptotic study is that to take the number of raw sample particles small relative to n, like if you take the number of particles to be 10 power 5, we're going to take the number of raw sample particles maybe only 100. In practical terms, you might want still to take M to be larger than the number of cores you have on a parallel machine, right? Because at the end of the day, you can parallelize the algorithm, but up to you can divide the CPU work into M independent tasks. And again, you have this single run variance estimate I mentioned briefly. Right, so sorry, Dang, it's your turn, I think. I let you speak, and I will stop the video, but I will go to next slide whenever you tell me.
Okay. Thanks, Nicolas.
You're welcome.
So can you move to the next slide, please? Because, yeah. Okay, so I'm going to present the numerical experiments that we have done in our paper. So the example that, the first example that we are looking at is something quite classic. So it is the logistic regression example. And we take the Sona dataset that you can find on the UCE site for machine learning. And we use the tempering sequence with automatic adaptation of the of intermediate temperatures. And for the MCMC steps, we use the random walk Metropolis. So again, the random walk Metropolis is something that works quite well if you calibrate the variance appropriately based on the current set of particles. So the experience that we ran is that we made multiple independent runs of standard SMC and waste-free SMC. We try to keep the computational cost the same between the two algorithms so that we would have some kind of a fair comparison. And so the two algorithms have approximately the same running time with n equal to 2 times 10 to the power 5 divided by k for the standard SMC and 2 times 10 to the power 5 for the waste-free version. So can you, yeah. So here are the figures that we got. So on the left, you have estimates from the waste-free SMC algorithm. And on the right, you have results from the standard SMC. So one striking feature here you can see for the waste-free SMC is that estimates are quite stable regardless of m, which is the number of resample particles that you take. So basically, what we're trying to say here is that provide that your m is much smaller than the total number of particles n, then the performance of the algorithm does not really depend on m. So on the right-hand side, you have the standard SMC estimates. And as you can see, it really depends on the number of MCMC steps k that you take. So if you take too few MCMC steps, k equal to 5, for example, you can see some estimator with a very large variances. And at the end, you see that the fact that you increase the number of MCMC steps so high actually destabilize your estimate. So you cannot choose k to be too small or either too big. You have to choose k somewhere in the middle at the right spot, and that is the inherent difficulty with standard SMC. Whereas with waste-free SMC, you do not have this kind of difficulty. So this is the same thing with yeah, I forgot to say that in the previous slide, what we are looking at is the mean of all marginals. So the marginal of the parameters that you are trying to estimate. Whereas in the next slide, we are looking at the log likelihood of the model. So on the next slide, yeah, we're looking at the log likelihood of the model. It's really something quite important for model selection, for example. So here you can see the same behavior of waste-free SMC and standard SMC. And for the optimal value of k in the previous slide, k equals to around 100. You can see a small bias here for standard SMC that we haven't been fully able to understand. But in any case, this means that calibrating standard SMC and getting reliable results from standard SMC may not be trivial. And waste-free SMC shows its advantage in this setting. And so here, yeah, here we look at the variance estimators based on the waste-free version. So as Nicolas has said before, one extra advantage of waste-free SMC is that you can have the variance estimator of the quantities that you output from the algorithm. So when you do Monte Carlo, it's quite important to estimate the error of the result that you give. And so here we have three different methods to estimate the result, estimate the variance of the result. So the first one is a quite simple method. You run the same algorithm for 10 times, and then you just take the empirical variance. Okay, and then the initial sequence estimator, the second one, is based on the initial sequence estimator for MCMC chains. So I will not detail it here, but you can look for more detail in the article. But basically, there is some direct, I mean, more or less direct translation from the corresponding method in the MCMC literature. And the last one is a method of estimation that is more specific for SMC models, but it is not very adapted here. So the main message that I'm trying to say is that if you want to estimate the variance of your estimator from weight-free SMC, then the best way seems to be using an init-sequence estimator, especially if your Markov chain is some kind of reversible Markov chain like random walk Metropolis. Okay, so I'll talk quite quickly about the second experiment, which is a little bit funny because it's more in the combinatorics world. So we moved to a quite different sample space, right? Before we were in the RD, and now we are in the space, in the discrete space of Latent squares. So what is a Latent square? A Latent square is a square of n rows, n columns, so that for each row you have all different digits from 1 to n. And for each column, you also have different digits from 1 to n. As you can imagine, generating such a Latent square is not as trivial as that, especially if the square starts to have some kind of large sizes. So our objective is to count the number of LD or Latent squares of size d. And for that, we design again a tempering sequence with different temperatures, lambda t. And the main feature of this tempering sequence is that if lambda t is about 0, is very small, then you have kind of a uniform distribution over the distribution of all the squares. And as lambda t becomes larger and larger, the distribution tends to the uniform distribution on the Latent square. And so by this sequence, you can use it to calculate what is called the normalizing constant. In this case, boils down to the number of Latent squares. Okay, and with respect to the MCMC kernels, we still use the classical Metropolis kernel, but adapted into this case. So the kernel is very simple. It's a proposal which consists of swapping two entries in a row. So again, we compare the performance between weight-free SMC and standard SMC, and we still use, we still calibrate M and K so that all algorithms have approximately the same running time. Okay, so here you can see that weight-free SMC becomes a little bit less reliable if you take M too big, but compared to the standard SMC, you can still see that the result given by weight-free SMC are much more correct. So we are working in dimension d equal to 11. This is the biggest d, so that the number of Latent squares is known exactly. Okay, so we can really compare the performance, and we can see again that weight-free SMC stays quite stable, whereas standard SMC works really bad if K is not big enough. Okay, so I will not go into detail for the third numerical experiment, but just to say that So the objective is to evaluate the Orson probability. So what I meant by Orson probability is the probability that a normal distribution is contained in some restrictive set. For example, here in the set of all points with a positive coordinate. You can look for the details in the paper, but the difference between this experiment and the two preceding ones, there are two differences. The first one is that the dimension of the distributions are increasing with respect to t. And the second one is that we use another MCMC kernel. We do not use the Metropolis Hastings kernel anymore, but we use the Gibbs one. Right, so I think I will come back to Nicolas for the conclusion.
Thank you very much, Dang. So to sum up, I mean, the part related to waste-free is we think it has the same advantages as standard SMC, meaning that it's automatable. I checked, it's a word and it exists. Maybe it's not such a common one. Hopefully you get the idea. You get estimate of the normalizing constant, which is not something you obtain easily from other methods. And it's really easy to make it parallel. And with Dang, I mean, we have two implementations. In both cases, we make it run on several CPUs. And if you have a large number of particles, you send only a small number of particles to each CPU, etc., etc. So that's very nice. But relative to standard SMC, we get something which is even more automatic because we don't have to choose K. And we get the single run of variance estimators. Okay. So, and a more general conclusion about SMC samplers, I hope I made you interested in this algorithm. Please try them. So Dang has his own implementation, which implement all the example on the paper, and the link is in the paper. Otherwise, I'm developing this Python library, and I've re-implemented the first numerical experiment of the paper. And this is a more general package where you have all kind of freeze relating to particle filters, resampling, etc. But you can do SMC samplers, both standard and waste-free. And you even have implemented something we have not talked before about using SMC for variable selection. And so if you're interested, there's a whole chapter about SMC samplers in this book I wrote with Miros. For waste-free, you should rather read this paper with Dang, which is on archive. And this is it. We're done. Thank you very much. Oh, I forgot to put my screen back actually.
Thank you. Thank you very much, Nicolas and Dang. And also thank you very much for sticking to your time.